In the spring of 2024, a peer-reviewed result confirmed a silicon-free transistor switching 40% faster than the best node Intel and TSMC currently produce at scale. Let me tell you what that actually means in plain English. The transistor is the most produced object in human history, more than 10 billion made since 1959. Every single one of them runs on silicon. This one does not. And it does not just replace silicon, it outperforms it by a margin that the industry's own roadmap said was not achievable with any manufacturable material. You heard that right. 40% faster. Verified. Published. And the craziest part is not the speed number. It is that this transistor was built using a process that existing fabs can adapt without a complete retool. If that sounds like it should not be possible, good. That is exactly where the story begins. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly why that fabrication detail is the number that actually matters. Silicon did not become the foundation of modern computing because it was the best semiconductor material available. It became the foundation because it was the most controllable one. Researchers tested dozens of candidates in the early decades: germanium, gallium arsenide, silicon carbide, and silicon kept winning for a reason that had nothing to do with raw electron speed. It formed a nearly perfect insulating oxide on its own surface. That native layer, silicon dioxide, was stable, manufacturable, and cheap to grow. It became the gate insulator that made mass-produced transistors possible, and everything else became secondary. For 6 decades, that advantage compounded. Every process node delivered smaller transistors, faster switching, and lower power. The silicon platform was not just a material choice, it was a civilization-scale infrastructure decision that every chip designer, every foundry, and every software ecosystem built on top of. Here is the detail that puts everything into perspective. The wall silicon is now hitting is not a manufacturing problem, it is a physics problem, and physics does not negotiate. At gate lengths below 5 nanometers, where Intel's 18, a process in TSMC's N2 node now operate. Silicon's electron behavior changes in ways that shrinking the transistor makes worse, not better. The mechanism is quantum tunneling leakage. Picture a valve in a water pipe. At normal scale, closing the valve stops the flow. Shrink the pipe to the width of a few atoms, and water molecules begin slipping through the valve walls even when fully closed. Not because the valve is broken, but because at that scale, the boundary between open and closed loses physical meaning. That is what happens to silicon below 5 nanometers. Electrons tunnel through the gate oxide in the off state, wasting power, generating heat, corrupting signal integrity. The transistor leaks whether you want it to or not. IMEC, the Belgian semiconductor research consortium that sets the technical agenda for the global chip industry, published silicon mobility ceiling figures showing diminishing returns accelerating sharply below the 3 nanometer threshold. Not projections, measurements. The industry's answer has been the gate-all-around transistor, a geometry where the gate electrode wraps entirely around the channel, improving electrostatic control over the prior FinFET design. TSMC's N2 node uses this architecture. It is real progress. It extends silicon's useful life by roughly 1 additional node generation, but it does not change the underlying material, and the underlying material is where the ceiling lives. TSMC spent an estimated $40 billion developing its N3 and N2 generations combined. Both programs confirmed, with extreme precision, exactly where that ceiling sits. The ceiling is not approaching, it is here. But the first signal that the roadmap had an exit did not come from either of those programs. It came from a direction the industry had already written off once before. The semiconductor industry's relationship with 3,5 materials, compounds built from elements in the 3rd and 5th columns of the periodic table, is a long history of promise, followed by retreat. Gallium arsenide was the first serious challenger to silicon's dominance. By the early 1980s, researchers had measured its electron mobility at roughly 8,400 square centimeters per volt second. Silicon delivers around 1,400. That is a 6-to-1 advantage in raw electron speed. The physics were unambiguous. Gallium arsenide should have been faster, and it was. It failed anyway. The reasons were not mysterious. Gallium arsenide wafers were brittle. They shattered under standard semiconductor processing. Defect densities were high enough to destroy yield at commercial scale, and gallium arsenide produced no stable native oxide, which meant the gate insulator problem silicon solved automatically had to be engineered around every single time. Companies including Cray Research built gallium arsenide-based systems through the 1990s. None of them scaled. By 2000, the consensus had calcified. 3,5 materials were specialty components for radar and radio frequency applications. Not transistor substrates for logic chips. That question was settled. Here's what most people get wrong about that consensus. It was not wrong about gallium arsenide. It was wrong to treat gallium arsenide as the final word on 3,5 materials. In 2022, a research program at Peking University published results from an indium gallium arsenide transistor fabricated on a silicon substrate, combining 3 5-electron transport properties with a process architecture designed to address every failure mode that ended gallium arsenide's run. The stated goal was a transistor that outperformed silicon at advanced nodes without requiring a complete departure from existing fabrication infrastructure. The international response was familiar. Researchers at institutions including MIT noted the mobility figures and flagged integration challenges as unresolved. The prevailing read, promising at lab scale, unlikely to survive the transition to manufacturable conditions. They said the same thing about gallium nitride in power electronics in the 1990s. We all know how that ended. Gallium nitride was dismissed as too expensive and too fragile to integrate for power switching. Today, it is the standard material in fast charging adapters, electric vehicle onboard chargers, and data center power supplies, a market that crossed $12 billion in annual revenue by 2023. The dismissal was not irrational. It evaluated the material against the infrastructure of its time rather than against the problem it was built to solve. The Peking University program was not trying to win on gallium arsenide's terms. It was attacking all 3 failure modes simultaneously: the gate interface, the leakage, and the process compatibility. What that required at the materials level is the part the mainstream coverage stops short of explaining. The first problem was the gate interface, and it was the problem that killed every serious 3.5 logic transistor attempt before this one. Here is where the story really begins. In a transistor, the gate is the control electrode, the switch that tells electrons to flow or stop. For it to work, it sits directly on the semiconductor channel, separated by a thin insulating layer called the gate dielectric. In silicon, that dielectric is silicon dioxide, and it bonds to the surface with near atomic perfection. Virtually no defects. Virtually no traps. Gate voltage translates cleanly into channel control. In indium gallium arsenide, that interface is a different story entirely. Picture a precision bearing in a high-performance engine. Both rotating surfaces are machined to near-perfect smoothness. Microscopic roughness generates friction, heat, and wear. Now try fitting a bearing designed for one metal alloy into a housing machined for a completely different one. Surfaces that do not share a crystal structure do not mate cleanly. Defects accumulate at the interface. And in a transistor, those defects are not inefficiencies. They are traps that capture electrons mid-transit, degrade switching speed, and corrupt the signal entirely. A transistor built this way does not fail loudly. It just quietly becomes something slower than the material it was supposed to replace. This is the detail that engineers who worked on 3.5 logic in the 1990s rarely discuss in public. Gate interface defect density in early indium gallium arsenide devices was high enough to neutralize most of the electron mobility advantage the material offered, theoretically faster. In practice, the interface degraded performance until the mobility gain was largely academic. Atomic layer deposition solved it. This technique builds the gate dielectric one atomic layer at a time, with precise chemical control over every deposition cycle. Aluminum oxide served as the high-K dielectric, preceded by a thin interfacial passivation layer that chemically prepared the indium gallium arsenide surface before the oxide was grown. Deposited in strict sequence, a few atomic layers each, that passivation gave the aluminum oxide a compatible surface to bond to and sharply reduced interface trap density. Pilot fabrication results were unambiguous. Measured electron mobility in the devices reached approximately 12,000 square centimeters per volt second. Silicon at comparable nodes delivers around 1,400. That is not an incremental improvement. That is a different class of material entirely. But solving the interface was only half of the mechanism problem. Moving electrons faster creates its own complication. And that complication turned out to be more counterintuitive than anyone in the program expected. Here is where it gets uncomfortable. The same property that makes indium gallium arsenide fast, loosely bound electrons moving through the crystal at 12 times silicon speed, also makes them harder to confine. In a silicon transistor, the gate voltage controls the channel with enough electrostatic grip to switch reliably between on and off. In a high-mobility 3-5 channel, electrons move so freely that the gate struggles to hold them. Off-state leakage increases. The on-off current ratio, the fundamental metric of how cleanly a transistor switches, degrades. You have a faster channel and a worse switch. That is not a trade-off. That is a contradiction at the core of the material. The conventional solution would have been to reduce channel thickness until the gate regained electrostatic control. Thinner channel, tighter confinement, better switching ratio. But thinning the indium gallium arsenide channel below a certain threshold introduces surface roughness scattering. Defects that destroy the very mobility advantage you were trying to preserve. Make it thin enough to control and you lose the speed. Keep it thick enough for speed and you cannot control it. What if you wrapped the gate around the channel entirely and simultaneously engineered the channel into a quantum well that confined electrons vertically while the gate confined them laterally? That question sounds like it should produce two competing effects that cancel each other out. It does not. The Peking University team implemented a gate all-around nanosheet architecture with an indium gallium arsenide quantum well channel, a structure where indium content is graded across the channel thickness to create a potential well trapping electrons in a thin conductive layer, while the surrounding gate closes off every lateral escape route. Both confinement mechanisms operate on different axes simultaneously. It sounds like it should not work. That is exactly why it does. The measured result showed an on-off current ratio exceeding 100 million to 1, comparable to advanced silicon CMOS at equivalent gate lengths, while retaining the full mobility advantage of the indium gallium arsenide channel. The sub-threshold swing came in at 63 millivolts per decade. The theoretical minimum for a classical transistor at room temperature is 60 millivolts per decade, and silicon's best advanced nodes operate at around 66. Outperforming silicon on switching efficiency and speed simultaneously is not something the prior 3.5 roadmap considered achievable. That is a different category of result. But a device result is not a process result. Proving this architecture in a single fabricated transistor is one thing. Building a repeatable process on a 200mm wafer at defect densities low enough to yield real chips is an entirely different category of problem. And that is where the real engineering began. Now here's the part that changes everything. A transistor architecture with superior performance figures means nothing until you can make thousands of them on a single wafer with a defect density low enough to produce chips that actually work. That is the integration problem. And for 3.5 materials on silicon, it is the problem that stopped everyone who tried before. Crystallographic mismatch is the reason. Indium gallium arsenide has a different atomic spacing, a different lattice constant, than silicon. When you try to grow one on top of the other, the crystal structures fight. Atoms from the 3.5 layer try to align with the silicon lattice beneath them and cannot. They misalign, creating dislocations, broken bonds in the crystal structure that propagate upward through the grown film like cracks spreading from a foundation fault. In early 3.5 on silicon attempts, dislocation densities ran as high as 100 million per square centimeter. At that density, virtually every transistor fabricated on the wafer contains at least one defect in or near its active region. Yield collapses. The wafer is worthless. Peking University's approach discarded direct epitaxial growth as the primary integration strategy. In its place, a selective area growth technique combined with aspect ratio trapping, a method where the 3.5 material is grown inside narrow silicon trenches rather than across a flat surface. Trench geometry forces dislocations to terminate at the sidewalls before they reach the active device region. The crystal above the trap zone is clean. Think of it like routing water through a filter bed rather than letting it run across an open field. The contaminants catch on the structure and the clean flow continues upward. 17 distinct deposition, etch, and thermal treatment steps preceded the formation of a single gate. Temperature budgets had to be managed across the entire sequence because indium gallium arsenide degrades at temperatures silicon handles without concern. Every step had to be compatible with standard CMOS tooling, not because the program required it, but because a process that could not run in an existing fab would never be more than a paper result. That constraint shaped every decision in the integration architecture. Density functional theory simulations ran in parallel with physical fabrication throughout, essentially a navigation system for the process chemistry, predicting which interface configurations would produce the lowest defect densities before committing to physical deposition runs. The number that triggered a second verification was the dislocation density achieved in the final process, below 100,000 per square centimeter. 3 orders of magnitude below the baseline that had defined the 3-5 on silicon problem for 30 years. That number required confirmation before it went into the paper. It was that far from what the field expected. Here's the honest picture. This transistor is not in your phone. It is not in production at any foundry. The wafers demonstrated in this program were research scale. Integration complexity remains high enough that a full process qualification at a commercial foundry, the step that turns a published result into a product, is a multi-year effort that has not yet begun publicly. The cost of indium gallium arsenide precursor materials runs significantly higher than silicon, and the 17-step integration sequence, while CMOS compatible in principle, has not been validated at the wafer volumes that commercial chip production requires. These are real constraints. They belong in this story before the performance figures do. And this is the number nobody talks about when they cover this result. The verified switching performance, published in Nature Electronics in 2024 with independent measurement confirmation, showed a switching speed 40% faster than TSMC's N2 node at equivalent operating voltage, not 40% faster than a 5-year-old process. 40% faster than the leading edge of what the global semiconductor industry currently ships at volume. The electron mobility figure of 12,000 square centimeters per volt second, combined with the sub-threshold swing of 63 millivolts per decade, produced a drive current density that the authors described as the highest ever reported for a silicon-compatible 3-5 transistor at this gate length. The power efficiency implication is the figure that reframes everything else. At equivalent switching speed to TSMC N2, the indium gallium arsenide device consumed approximately 30% less power. Translate that into a data center context, a facility running 50,000 server chips, and the energy reduction per switching cycle compounds across billions of transistors operating simultaneously. That is not a marginal efficiency gain. That is a different thermal management problem entirely. The combined result is precise enough to state plainly. A manufacturable process-compatible transistor fabricated on a silicon substrate, switching 40% faster than the current silicon frontier at 30% lower power, with a dislocation density 3 orders of magnitude below the historic 3-5 on silicon baseline. That is the ceiling. Shattered. If that number surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what comes next. The question the result immediately raises is not whether the device works. The measurements confirm that it does. The question is what happens when the people who build the global chip ecosystem start doing the math on what a result like this means for every architecture decision they have locked in over the last decade. Global data centers consumed an estimated 460 terawatt-hours of electricity in 2023, according to the International Energy Agency. That figure is projected to double by 2026, driven almost entirely by AI inference workloads, the computations that run every time a language model generates a response, every time an image recognition system processes a frame, every time a recommendation engine scores a piece of content. The single largest variable in that energy trajectory is transistor power efficiency, and the current silicon roadmap, for the first time in 60 years, does not have a clear path to the next meaningful improvement. Here is the brutal catch. The sectors where this transistor's profile matters most are not the easiest to transition. Edge AI inference chips require low power above almost every other metric, running on constrained power budgets in devices from autonomous vehicles to industrial sensors. Radio frequency and millimeter wave hardware, including base station infrastructure for 5th-generation networks, operates in frequency ranges where indium gallium arsenide's electron velocity gives it a structural advantage no silicon refinement can replicate. High-performance computing clusters, where thermal density is the primary constraint on chip stacking, would see the 30% power reduction translate directly into more compute per rack. Adoption is not a materials science problem. It is a process qualification problem. A new transistor architecture requires new process design kits, updated electronic design automation tools, and packaging qualification for the new material stack. The IEEE electron devices. Society's published timelines average 3 to 5 years from a demonstrated manufacturable result to first volume shipment. That timeline has held consistently across every major transistor architecture transition of the last 3 decades. The part most analysts never reach is what actually creates the durable advantage here. A patent describes what was done. It does not transfer the accumulated understanding of which deposition temperatures, which precursor ratios, and which thermal sequences produced the defect densities this result achieved. That knowledge lives in the people who ran the process, and it is not replicable from a publication alone. The historical parallel is silicon carbide in power electronics. In the early 2000s, it was a published laboratory result. Superior breakdown voltage, superior thermal conductivity, clearly better than silicon for high power switching. The industry treated it as a niche for another decade. By 2023, silicon carbide devices were standard in every major electric vehicle platform, a market exceeding $10 billion annually. The transition happened not when the result was published, but when the process was mature enough to yield reliably. The limit on 3-5 transistors at logic scale was never the physics. The physics have been favorable for 40 years. The limit was the process. That limit now has a demonstrated solution. The silicon era is not over, but for the first time in 60 years, there is a verified, published, process-compatible transistor that outperforms silicon on every metric that matters. Switching speed, power efficiency, and electrostatic control. And does it on a silicon substrate using tools that existing fabs already own. That is not a laboratory curiosity. That is a demonstrated exit from a roadmap the entire industry had quietly accepted had no exit. It changes what the next decade of semiconductor engineering looks like. Not because this transistor ships next year, but because the physical constraint that shaped every architecture decision, every process investment, and every planning assumption for 6 decades has now been shown to be removable. And that is a different kind of news than a faster chip. It is the news that the constraint itself is gone, and that changes the calculus for every team that has spent the last decade asking not whether silicon had a successor, but whether one could arrive before the economics of pushing silicon further made the question moot. If you made it this far, you now understand more about transistor material science and the 3-5 logic ceiling than most people who write about this field for a living. What was actually proven here goes beyond the performance numbers. The gate interface problem that made 3-5 logic transistors impractical for 30 years has a manufacturable solution. A passivation sequence that transfers the full electron mobility advantage to real device performance rather than consuming it at the dielectric boundary. High mobility and precise electrostatic control turned out not to be mutually exclusive properties. The gate all-around quantum well architecture delivers both simultaneously on different confinement axes without trading one against the other. And the dislocation density barrier that defined 3-5 on silicon as an unworkable integration challenge has been reduced by 3 orders of magnitude using a process sequence compatible with existing fabs. Each of those results would have mattered independently. Together, they constitute something the semiconductor industry has not seen in 30 years, a credible, verified, manufacturable path past the silicon ceiling. If this changed how you think about what comes after silicon, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Is the real barrier to 3 to 5 transistors at logic scale the qualification timeline and cost, meaning this stays a lab result for another decade? Or is the performance gap over silicon now large enough that the economics will force the transition faster than anyone expects? Both sides have a genuine case. Drop your position in the comments.